13.8 billion years ago, there was nothing. No space, no time, no matter, no energy, not even darkness, because darkness requires space to exist within. There was an inconceivable void beyond human comprehension. There was nothing. Then, in an instant smaller than a trillionth of a second, faster than thought, faster than light, faster than the very concept of speed itself, everything exploded into existence. This is the Big Bang Theory, the cornerstone of modern cosmology, accepted by nearly every physicist on Earth. It explains the birth of the first stars igniting in the primordial darkness, the formation of galaxies spiraling through the cosmic void, the creation of every single atom in your body, the carbon in your muscles that allows them to contract, the calcium in your bones that keeps you upright, the iron in your blood that carries oxygen to your brain. All of it forged in the hearts of dying stars, born from the primordial fireball that began everything. But here's what keeps scientists awake at night, staring at equations scrawled on whiteboards at 3 in the morning. We cannot see the Big Bang. We cannot recreate it in any laboratory on Earth. We cannot build a time machine to travel back 13.8 billion years and witness it. Every single piece of evidence is indirect, ancient light from the edge of the observable universe, whispers of microwave radiation filling what we call empty space, mathematical models built on assumptions that may or may not reflect reality. In July 2022, the James Webb Space Telescope, a $10 billion instrument orbiting 1 million miles from Earth, the most powerful observatory ever built, detected something that sent shockwaves through the astronomical community. Galaxies that shouldn't exist according to our models. Fully formed spiral structures appearing just 300 million years after the Big Bang. Too mature, too organized, too massive, too luminous, too soon. According to our best models of galaxy formation, these cosmic islands should be chaotic clouds of gas, still assembling their first generation of stars through violent, turbulent processes. Instead, they look like the Milky Way did billions of years later, structured, stable, ancient, impossibly well-developed for their young age. One prominent astronomer described it as finding a fully grown oak tree in a nursery of seedlings. Another called it panic-inducing. A third wondered aloud whether our fundamental assumptions about cosmic time might be wrong. What if the greatest scientific theory of our time, tested, refined, and confirmed by a century of observations, is incomplete? What if the universe is older than we think, ancient beyond our measurements, stretching back into a past we cannot fathom? What if the Big Bang, as we understand it, never happened at all? What if everything we've built our cosmic worldview upon is just the opening chapter of a far stranger story that challenges the limits of human understanding? Today, we journey through evidence that challenges everything we thought we knew about the origin of the universe. We'll examine the proof that changed physics forever, and the anomalies that threaten to unravel it all. We'll meet the scientists who discovered the afterglow of creation, the mathematicians who predicted the impossible, the observers who found cracks in the foundation of cosmology. We'll explore the profound mysteries that remain unsolved, the nature of dark energy, the origin of cosmic structure, the possibility of other universes beyond our own. We'll venture into questions that breach the boundaries of science and enter the realm of philosophy itself. Why does anything exist at all? Why these laws of physics and not infinitely many others? Are we alone in an infinite cosmos, or just one bubble in an endless multiverse where every possibility becomes reality? The answers will challenge your understanding of time, space, and existence itself. Prepare yourselves. The journey begins now. To understand whether the Big Bang is true, whether the universe truly had a beginning or has existed eternally, we must first travel back nearly a century, to 1929, to Mount Wilson Observatory perched high above Los Angeles. There, at 5,710 feet elevation, isolated from the city lights below, a quiet, meticulous astronomer named Edwin Hubble was about to shatter humanity's most fundamental assumptions about existence itself. For millennia, since humans first looked up at the night sky and wondered about their place in the cosmos, we believed the universe was static and eternal. The stars were fixed in the celestial sphere, unchanging points of light wheeling across the heavens in predictable cycles. The cosmos was permanent, perfect, perhaps even divine in its constancy. Aristotle taught it 2,300 years ago. Medieval scholars incorporated it into theology. Victorian astronomers assumed it. Even in the 20th century, as physics underwent revolutionary changes with relativity and quantum mechanics, the greatest minds still assumed the universe had always existed in essentially its current form and always would. Albert Einstein himself, perhaps the greatest physicist who ever lived, was so deeply convinced of this eternal, static cosmos that when his own equations, the field equations of general relativity published in 1915, predicted a dynamic universe that must either expand or contract, he refused to believe them. The mathematics was clear, but Einstein's philosophical commitment to an eternal universe was stronger. So he modified his equations, adding a mathematical term he called the cosmological constant, represented by the Greek letter lambda, specifically designed to counteract gravity and keep the universe frozen in place, neither expanding nor contracting. It was an ad hoc fix, a fudge factor, and Einstein knew it. He reportedly called it his greatest blunder, though whether he actually used those words or whether it's apocryphal remains debated by historians. But Edwin Hubble, working night after lonely night at the 100-inch Hooker telescope, then the largest optical telescope on Earth, a technological marvel with a mirror weighing 4.5 tons, observed something extraordinary that would demolish this comfortable, ancient worldview forever. Hubble wasn't looking for a cosmic revolution. He was simply trying to measure distances to what astronomers called spiral nebulae, those fuzzy, pinwheel-shaped objects scattered across the sky. Most astronomers believed these nebulae were clouds of gas within our own Milky Way galaxy. Hubble suspected otherwise. Using Cepheid variable stars as distance indicators, stars that pulsate rhythmically with periods directly related to their intrinsic brightness, Hubble proved that these nebulae were actually distant galaxies, separate island universes millions of light-years beyond our own galaxy. This alone would have secured his place in history. But Hubble went further. Using a technique called spectroscopy, breaking starlight into its component wavelengths using prisms or diffraction gratings, Hubble could examine the detailed fingerprints of light from these distant galaxies. When light passes through or is emitted by specific elements, it creates characteristic patterns of bright and dark lines at very specific wavelengths. These spectral lines are like barcodes. Each element produces a unique pattern burned into the laws of quantum mechanics. Hydrogen creates absorption lines at 656.3 nanometers, the red H-alpha line, 486.1 nanometers, the blue H-beta line, and other precise wavelengths. Helium has its own pattern. So do oxygen, iron, calcium, sodium, and every other element. By identifying these patterns, astronomers can determine what distant objects are made of, their chemical composition, even across billions of light-years of space, even across spans of time longer than the Earth has existed. But when Hubble examined the spectra of distant galaxies, he noticed something peculiar, something that violated all expectations about a static universe. The spectral lines weren't where they should be. They were shifted, displaced toward the red end of the spectrum. The hydrogen line that should appear at 656.3 nanometers appeared at 660 nanometers. Or 670. Or 700. Always shifted toward longer wavelengths, toward the red. Red light has a longer wavelength than blue light, about 700 nanometers compared to blue's 450 nanometers. This shift toward red wavelengths is called, appropriately, redshift. And redshift has only one explanation in classical physics: motion. It's the Doppler effect, the same phenomenon that makes a siren's pitch drop as an ambulance speeds past you. Motion away from the observer stretches waves, shifts them toward longer wavelengths. For sound, motion away lowers the pitch. For light, motion away shifts the color toward red. The redshift meant one thing, and one thing only: these galaxies were moving away from us. Flying away through space at tremendous speeds, hundreds, thousands of kilometers per second. Now you might think, so what? Maybe we're at the center of the universe, and everything's fleeing from the Milky Way. Maybe we're some cosmic pariah, shunned by the rest of the universe in some kind of galactic exile. But here's where it gets truly strange, where the comfortable, intuitive universe shatters completely and something far more bizarre emerges. Hubble didn't just find that galaxies were moving away from us. He discovered they were moving away in proportion to their distance. This relationship is now called Hubble's law. A galaxy 10 million light-years away might be receding at 700 kilometers per second. A galaxy 20 million light-years away, twice as far, was moving away at 1,400 kilometers per second, twice as fast. A galaxy 100 million light-years distant was receding at 7,000 kilometers per second, 10 times faster than the first. The mathematical relationship is beautifully simple. V equals h times d, where v is recession velocity, d is distance, and h is the Hubble constant, currently measured at approximately 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. Imagine dots painted on the surface of a balloon. As you inflate it, every dot moves away from every other dot. Pick any dot and call it us. From that dot's perspective, all other dots are receding. The farther apart two dots are, the faster they separate, not because they're moving through the rubber surface, but because the surface itself is stretching, expanding uniformly in all directions. This is cosmic expansion. Galaxies aren't flying through space like shrapnel from an explosion, not pieces of debris scattered by some blast in a pre-existing void. Space itself is expanding, carrying galaxies along like boats on a swelling ocean, like raisins in rising bread dough. And here's the crucial insight: if you're on any galaxy, you see exactly the same thing. Every galaxy observes all other galaxies receding, with velocity proportional to distance. There is no center. There is no edge. The expansion happens everywhere, uniformly. This observation was revolutionary, paradigm-destroying, mind-bending in its implications. If galaxies are flying apart today, pulled by the expansion of space, they must have been closer together yesterday. Rewind the cosmic movie by 1,000,000 years, and galaxies are slightly closer. Rewind 1 billion years, and they're much closer, the universe denser, hotter. Rewind 10 billion years, and galaxies haven't even formed yet, the universe is a thin soup of hydrogen and helium. Rewind far enough, all the way back, and everything in the observable universe, every atom, every particle, every quantum of energy, would converge to a single mathematical point. A cosmic egg. A primordial seed. A singularity of infinite density and infinite temperature where the known laws of physics break down completely, where space and time themselves cease to have meaning. The Belgian priest and physicist Georges Lemaitre had actually predicted this independently in 1927, 2 years before Hubble's definitive observations. Lemaitre, working from Einstein's field equations, realized that a static universe was unstable. It must be either expanding or contracting. He proposed what he called the primeval atom, or cosmic egg, the hypothesis that the universe began from an initial point of enormous density. When British astronomer Fred Hoyle, an outspoken critic of the idea, later described it mockingly on BBC Radio in 1949, he sarcastically called it this Big Bang idea. The name stuck, despite Hoyle's intention to ridicule it. To this day, the theory carries a name given to it by one of its greatest opponents. Hubble's discovery implied something profound, something almost philosophically uncomfortable. The universe had a beginning. It wasn't eternal. It was born. There was a first moment, a moment zero, when time itself began ticking, when the cosmic clock started running. Before that moment, the question may be meaningless. Time itself didn't exist. There was no before. But scientists are trained skeptics. A single line of evidence, no matter how compelling, is never enough. They needed more. They needed independent, convergent confirmation. They needed something that could only exist if the Big Bang actually happened. Some relic, some fossil, some tangible fingerprint of creation that no alternative theory could explain away. They got it 35 years later, in the most unexpected way imaginable, from 2 engineers who weren't even looking for it. In 1964, 2 radio astronomers at Bell Laboratories in Homedale, New Jersey, Arno Penzias and Robert Wilson, were trying to eliminate an annoying source of noise from their horn-shaped radio antenna. They were preparing the antenna, originally built for satellite communications with the Echo and Telstar satellites, for radio astronomy observations. But this persistent, maddening static was ruining their measurements. The noise wasn't coming from any identifiable source. It wasn't directional. It came from every direction they pointed the antenna: north, south, east, west, straight up, toward the horizon. The hiss persisted day and night, summer and winter, spring and fall. It was omnipresent, omnidirectional, invariant with time, like a whisper that filled the entire sky uniformly. The intensity was always the same, equivalent to about 3.5 Kelvin of thermal radiation, just 3.5 degrees above absolute zero. Penzias and Wilson were meticulous experimentalists. They considered every possible explanation. Maybe it was radio interference from New York City, just 30 miles away, bleeding into their sensitive equipment. They tested that hypothesis. The signal didn't correlate with time of day or direction toward the city. Maybe it was electrical noise from their own equipment, some subtle malfunction generating spurious signals. They systematically tore the system apart, tested every circuit, replaced every component, checked every connection. Nothing changed. They even found that pigeons had nested inside the horn antenna, coating it with what the scientific literature politely calls white dielectric material, pigeon droppings. Penzias and Wilson meticulously cleaned out the nesting material, trapped the pigeons, relocated them 30 miles away, cleaned the antenna again when the pigeons returned, and eventually resorted to more permanent solutions. Still, the noise persisted, unchanged. They were on the verge of publishing a paper about mysterious microwave interference of unknown origin when Penzias mentioned it to a colleague, who mentioned it to another physicist, who said, "You should call Bob Dick at Princeton." Robert Dick was a legendary physicist at Princeton University, just 40 miles away. When Penzias called and described the signal, Dick listened carefully. Then he hung up the phone, turned to his research group, and said, "Boys, we've been scooped." Dick's team had been preparing to search for exactly what Penzias and Wilson had accidentally discovered: the afterglow of creation itself. The echo of the Big Bang. Here's the physics, the theoretical prediction that made this discovery so profound. If the universe began in an extremely hot, dense state, a fireball of pure energy, a seething plasma where matter and radiation were inextricably mixed, it would have been filled with intense, high-energy electromagnetic radiation. Imagine the entire observable universe, containing all its mass and energy, compressed into a region smaller than an atom. The temperature would be incomprehensibly hot, trillions of degrees. At such temperatures, atoms cannot exist. Even atomic nuclei cannot exist. Matter would be broken down into a plasma of elementary particles, quarks, electrons, photons, all interacting violently. As space expanded according to Hubble's law, this fireball would cool. The wavelengths of all that radiation would stretch along with space itself. Think of light as waves painted on a rubber sheet. As you stretch the sheet, the waves stretch too. Their wavelength increases, which for electromagnetic radiation means they shift toward the red end of the spectrum and beyond. Light that began as ultra-high-energy gamma rays, wavelengths of 10 to the power of -12 meters, would redshift to X-rays, then ultraviolet, then visible light, then infrared, and finally, after 13.8 billion years of cosmic expansion, to microwaves, wavelengths of about 1 millimeter. In 1948, physicists George Gamow, Ralph Alpher, and Robert Herman made a precise quantitative prediction. This cosmic background radiation should still exist today, permeating all of space uniformly, cooled to approximately 5 degrees above absolute zero, 5 Kelvin. Robert Dick, working independently in the 1960s, refined this calculation to about 3 Kelvin and was building specialized equipment to detect it. Penzias and Wilson had measured 3.5 Kelvin, later refined with better calibration to 2.725 Kelvin. The match was extraordinary, theory predicting observation to within 30%. This was the smoking gun. The cosmic microwave background, or CMB, is a baby picture of the universe taken when the cosmos was only 380,000 years old, an infant, just beginning to become transparent to light. Before that moment, called recombination, The universe was opaque, like being inside a star. The temperature was about 3000 Kelvin, hot enough to ionize hydrogen, keeping electrons and protons separate. Photons couldn't travel freely because they constantly scattered off these free electrons, like light scattering in fog. But as the universe expanded and cooled past 3000 Kelvin, protons and electrons combined to form neutral hydrogen atoms. Suddenly, photons could stream freely through space without scattering. The universe became transparent. Those photons have been traveling ever since, for 13.8 billion years, gradually cooling and redshifting as space expanded. That ancient light still fills the universe today. It comes from every direction uniformly. It's the oldest light in the universe, a snapshot of the moment when the cosmos first became visible. When you tune an old analog television between channels and see static, that salt and pepper snow on the screen, about 1% of that static is caused by CMB photons hitting the antenna. You're literally seeing the echo of the Big Bang with your own eyes, billions of photons that began their journey before the Earth existed, before the Sun existed, before any stars had formed. For this discovery, Penzias and Wilson won the 1978 Nobel Prize in Physics, one of the most deserved Nobel Prizes in history. The Big Bang Theory moved from provocative speculation, an interesting but controversial idea, to mainstream scientific consensus, accepted by virtually the entire physics community. The universe, it seemed clear, had a history. It had a beginning. It evolved over time. The case appeared closed. But the evidence forces us to confront an uncomfortable possibility. If we can detect the universe at 380,000 years old, capturing its baby picture, what happened before that? What happened in those first 380,000 years of cosmic history? What occurred in the first second, the first microsecond, the first incomprehensibly brief instant after time began? What triggered the Big Bang itself? And perhaps most mysteriously, why does the cosmic microwave background show patterns, subtle temperature variations of 1 part in 100,000, that seem to suggest the universe was somehow fine-tuned, carefully calibrated for the eventual emergence of stars, galaxies, planets, and life? The discovery of cosmic expansion through Hubble's observations and the detection of the cosmic microwave background seemed to seal the case definitively. Two independent lines of evidence, predicted by theory decades before observation, confirmed by meticulous experimental work. The Big Bang Theory wasn't just a good idea, it was scientifically validated reality. Case closed. Question answered. Mystery solved. Or so it seemed. But science doesn't deal in absolute certainty or final answers. It deals in evidence that can be tested, challenged, refined, and overturned if new observations demand it. And as telescopes grew larger and more powerful, as detectors became more sensitive, as satellites mapped the heavens with ever greater precision, scientists found something profoundly unsettling lurking in the data. The universe didn't just obediently follow predictions. It defied them. It showed anomalies, contradictions, impossible features. It revealed mysteries that standard Big Bang cosmology couldn't explain, problems so deep that they threatened the entire framework. The evidence forces us to confront an uncomfortable truth. Everything we've discovered so far, Hubble's expansion, the cosmic microwave background, the age of the universe, is only the opening chapter of a far stranger, far more mysterious story than anyone imagined. A story that's still being written. The Big Bang Theory doesn't rest on one or two observations, no matter how compelling. In science, a robust theory requires multiple independent lines of evidence. Different phenomena, measured by different methods, in different eras, all converging on the same conclusion. Think of it like a criminal investigation. A single witness is interesting but insufficient. But if you have DNA evidence, fingerprints, security camera footage, financial records, and multiple witnesses who don't know each other all telling the same story, then you have a case beyond reasonable doubt. The Big Bang Theory has that kind of support. Let's examine the pillars of evidence one by one, from the most concrete and measurable to the most profound and mysterious. In 1948, a young physicist named Ralph Alpher was working on his PhD thesis at George Washington University under the supervision of George Gamow, one of the most brilliant and eccentric minds in 20th century physics. Gamow, a Russian émigré who had fled Stalin's Soviet Union, was known for his penetrating physical intuition, his humor, and his bold, sometimes outrageous ideas. Alfer and Gamow tackled a fundamental question. If the universe began in a hot, dense state, what happened in the first minutes? They realized that, at the enormous temperatures and densities of the early universe, nuclear fusion must have occurred. Not in stars, which didn't exist yet, but in the primordial fireball itself, throughout all of space simultaneously. Here's the timeline they calculated. At 1 microsecond after the Big Bang, the temperature was about 10 trillion Kelvin, 10 to the power of 13 K. At these energies, quarks and gluons swarmed in a quark-gluon plasma, too hot and energetic to bind into protons and neutrons. By 1 millisecond, temperature had dropped to about 1 trillion Kelvin. Quarks combined into baryons, protons and neutrons. At 1 second, temperature reached about 10 billion Kelvin. The universe was a seething mix of photons, electrons, positrons, neutrinos, protons, and neutrons, all in thermal equilibrium. Between 1 second and 3 minutes, the conditions were perfect for nuclear fusion. Temperature ranged from 10 billion down to about 1 billion Kelvin. Hot enough for nuclear reactions but cool enough for some nuclei to survive without being immediately photodisintegrated. Here's how it unfolded. First, protons, hydrogen nuclei, and neutrons began combining to form deuterium, heavy hydrogen with 1 proton and 1 neutron bound together. But deuterium is fragile. At high temperatures, photons can easily break it apart. Only when the universe cooled below about 1 billion Kelvin could deuterium survive long enough for the next step. Then deuterium nuclei captured additional neutrons or fused with other deuterium nuclei to form helium-3, 2 protons, 1 neutron, and helium-4, 2 protons, 2 neutrons. The stable helium that makes up about 10% of the Earth's atmosphere and most of what's inside party balloons. Some helium-4 nuclei captured additional neutrons to form lithium-7, 3 protons, for neutrons. But by about 20 minutes after the Big Bang, the universe had expanded and cooled too much. The temperature dropped below the threshold needed for fusion, and the density of particles became too low. The nuclear furnace of the primordial universe shut down, leaving a universe composed of approximately 75% hydrogen, by mass, 25% helium, 4 trace amounts of deuterium, about 0.0025%, trace amounts of helium-3, about 0.0001%, trace amounts of lithium-7, about 10 to the power of -9. Alfer and Gamow made these predictions in 1948, decades before technology existed to test them precisely. They were doing theoretical physics at its most audacious, predicting the chemical composition of the entire universe based on nuclear physics and the assumption of a hot Big Bang. When observational astronomy finally caught up in the 1960s and 1970s, astronomers measured the chemical composition of the oldest observable stars, population 3 stars, stars that formed very early in cosmic history from nearly pristine primordial gas with almost no contamination from previous stellar generations. The measurements matched the predictions with stunning accuracy. Hydrogen, 75%, predicted 75%. Helium-4, 25%, predicted 25%. Deuterium, 0.0025%, predicted 0.0025%. Helium-3, 0.0001%, predicted 0.0001%. Lithium-7, about 10 to the power of -9, predicted 10 to the power of -9. Though there's a troubling discrepancy here we'll return to later. This isn't something you can fake, explain away, or dismiss as coincidence. The abundances of these light elements depend on incredibly precise conditions in the early universe. The baryon-to-photon ratio, how many protons and neutrons per photon, the expansion rate determined by the total energy density, the temperature evolution governed by thermodynamics, the precise nuclear reaction rates measured in laboratories. Change any of these parameters even slightly, and you get wildly different element abundances. If the universe expanded faster, less helium would form. If it expanded slower, almost all hydrogen would convert to helium. If the baryon density were different, all the ratios would shift. Getting this right is like predicting the exact number of red, blue, and yellow candies in a jar by calculating the factory process that mixed them. Except the jar is the entire universe, the factory process is nuclear physics at 1 billion degrees, and the calculation spans the first 20 minutes of existence. The probability of getting these ratios correct by chance, without the Big Bang being fundamentally true, is essentially zero. This is quantitative, precise, testable prediction and confirmation, the gold standard of scientific validation. Big Bang nucleosynthesis isn't just evidence for a hot, early universe. It's a precise calibration tool, allowing cosmologists to measure fundamental parameters like the total amount of normal matter in the universe. The evidence is overwhelming. But there's more, much more. The cosmic microwave background isn't just a uniform glow at 2.725 Kelvin filling the sky. If it were perfectly uniform, if every point had exactly the same temperature with no variations whatsoever, the universe would still be a thin, featureless soup of hydrogen. No stars would exist. No galaxies. No planets. No life. No one to ask questions about cosmology. In 1992, the COBE satellite, Cosmic Background Explorer, launched by NASA and operated by a team led by John Mather and George Smoot, detected something extraordinary. Tiny temperature fluctuations in the CMB, variations of only 1 part in 100,000, or about 30 microkelvin. These aren't noise or measurement errors. They're real physical temperature differences from the early universe, the seeds of all cosmic structure. When Smoot announced the COBE results at a scientific meeting, he said it was like seeing the face of God, a statement that made headlines but also irritated many of his more secular colleagues. Stephen Hawking called it the discovery of the century, if not of all time. What do these fluctuations represent? Imagine the early universe as an ocean of hot plasma, a mix of protons, electrons, and photons all interacting. Gravity tried to pull matter together into denser clumps. But radiation pressure, the outward push of photons, resisted that collapse, pushing matter apart. This created sound waves, actual acoustic oscillations propagating through the primordial plasma at about 60% the speed of light. Regions compressed by these sound waves became slightly denser and hotter. Regions rarefied became slightly less dense and cooler. These acoustic oscillations, sound waves in the early universe, created a specific pattern of hot spots and cold spots of specific sizes. When recombination occurred at 380,000 years, when electrons and protons combined to form neutral hydrogen, and the universe became transparent, these sound waves froze in place, imprinted on the CMB like ripples on a pond captured mid-motion. In 2003, the Wilkinson Microwave Anisotropy Probe, WMAP, a more advanced satellite named after pioneering cosmologist David Wilkinson, mapped these fluctuations in stunning detail across the entire sky. The resolution was 33 times better than COBE. In 2013, the European Space Agency's Planck satellite refined the measurements even further, with resolution and sensitivity surpassing WMAP. What they found was remarkable. The fluctuations aren't random. They show a specific pattern of scales, a power spectrum with distinct peaks at specific angular sizes. The first peak, the largest, most prominent, corresponds to regions that had just completed one compression cycle when recombination occurred. These were the regions that were maximally compressed, at their densest and hottest. The second peak represents regions at maximum rarefaction, stretched out, at their least dense and coolest. The third peak shows regions that had completed 1.5 cycles. The positions and heights of these peaks encode fundamental information about the universe. The geometry of space, flat, curved, saddle-shaped, the total density of matter, the ratio of normal matter to dark matter, the amount of dark energy, the Hubble constant, expansion rate, even subtle effects like the number of neutrino species. When cosmologists fit theoretical models to the Planck data, they can determine these parameters with extraordinary precision. Age of the universe, 13.797 plus or minus 0.023 billion years. Hubble constant, 67.4 plus or minus 0.5 kilometers per second per mpc. Baryon density, 4.9% of the total energy density. Dark matter density, 26.8% dark energy density, 68.3% spatial curvature, flat to within 0.4%. The The CMB is a Rosetta Stone for cosmology, a treasure trove of information about cosmic history encoded in temperature variations 100,000th the size of typical fluctuations. And the pattern matches Big Bang predictions with breathtaking precision. If the Big Bang theory is correct, those tiny ripples in the CMB at 380,000 years should directly correspond to the distribution of galaxies we observe today, 13.8 billion years later. Dense regions in the early universe, the hot spots in the CMB, should have attracted more matter through gravity, eventually collapsing to form the first stars, then galaxies, then clusters and superclusters of galaxies. Less dense regions should have become cosmic voids, vast empty spaces between galactic structures. This is a bold, testable prediction. The pattern at 380,000 years should determine the pattern 13.8 billion years later. In the 1980s and 1990s, astronomers undertook heroic observational campaigns to map the three-dimensional distribution of galaxies. The Center for Astrophysics Redshift Survey, led by Margaret Geller and John Huckra, mapped thousands of galaxies. The 2-degree Field Galaxy Redshift Survey in Australia mapped hundreds of thousands. And eventually, the Sloan Digital Sky Survey, one of the most ambitious astronomical projects in history, mapped millions of galaxies across a quarter of the sky. What they found was absolutely breathtaking. Galaxies aren't scattered randomly through space like stars sprinkled across the night sky. They form an intricate cosmic web, a vast lacework of filaments and walls surrounding enormous voids. Galaxies cluster along these filaments like cities along highways, like lights along the threads of a spider's web. Where multiple filaments intersect, massive galaxy clusters form, gravitationally bound structures containing hundreds or thousands of galaxies, with total masses up to 1,000,000 billion times the mass of our Sun. The largest known structures are almost incomprehensibly vast. The Sloan Great Wall, discovered in 2003, spans 1.37 billion light-years, a wall of galaxies so large that light takes 1.37 billion years to travel from one end to the other. The Hercules Corona Borealis Great Wall, found in 2013, spans roughly 10 billion light-years, nearly a tenth of the observable universe. It's so large that it arguably shouldn't exist according to our models, posing yet another challenge to cosmology. And the voids, the empty spaces, are equally staggering. The Boötes Void, discovered in 1981, is 330 million light-years in diameter and contains only 60 galaxies where thousands should exist. It's so empty that one astronomer called it a hole in the universe. Now here's the critical test. When scientists compared this observed galaxy distribution to the pattern of fluctuations in the CMB, they found an almost perfect match. Using sophisticated computer simulations, running on some of the world's most powerful supercomputers, researchers can grow the universe virtually. They start with the CMB pattern at 380,000 years, input the laws of gravity and physics, and let the simulation run forward through cosmic time, watching as tiny density fluctuations amplify through gravitational collapse. The Millennium simulation, run in 2005, tracked 10 billion particles through 13 billion years of cosmic evolution. The Illustra simulation, completed in 2014, modeled the formation of galaxies with unprecedented detail, including gas dynamics, star formation, and supermassive black holes. The results are stunning. These simulations produce a cosmic web structure virtually identical to what we observe. The filaments, the voids, the clusters, all emerge naturally from the CMB initial conditions through gravity alone. The seeds planted in the CMB 13.8 billion years ago grew, through the relentless pull of gravity over billions of years, into the magnificent architecture of the cosmos we see today. This is independent, convergent confirmation of Big Bang cosmology from a completely different direction. The early universe's pattern predicts the late universe's structure, and observation confirms the prediction with extraordinary precision. Here's another key prediction. If the universe has a history, if it evolves over time rather than existing eternally in the same state, then galaxies at different distances should look different, because we're seeing them at different ages. Light travels at 299,792 kilometers per second. Fast, but not infinitely fast. That means when we look at distant objects, we're looking back in time. The light from the sun takes 8 minutes and 20 seconds to reach us. We see it as it was 8 minutes ago. If the sun exploded right now, we wouldn't know for 8 minutes. The nearest star beyond our solar system, Proxima Centauri, is 4.24 light-years away. We see it as it was 4.24 years ago. When it's October 2025 here, we're seeing Proxima as it was in July 2020. The Andromeda Galaxy, our nearest large galactic neighbor, is 2.5 million light-years away. When we photograph Andromeda, we're seeing light that left that galaxy 2.5 million years ago, when early hominids were just beginning to evolve in Africa, when Homo habilis was learning to make stone tools. The Hubble Space Telescope's deep field observations, some of the most famous images in astronomy, pushed this time machine to its limits. The original Hubble Deep Field, captured in 1995 by pointing the telescope at a tiny, apparently empty patch of sky for 10 continuous days, revealed about 3,000 galaxies in an area the size of a pinpoint held at arm's length. Most of these galaxies were so distant that their light had been traveling for 12 to 13 billion years. We were seeing them as they appeared just 700 million to 1 billion years after the Big Bang, galaxies in their infancy. And here's what those images revealed: young galaxies look dramatically different from modern ones. They're smaller, typically just a few thousand light-years across compared to the Milky Way's 100,000 light-years. They're bluer, indicating active star formation with massive, short-lived blue stars. They're more irregular and chaotic in shape, lacking the elegant spiral arms or smooth elliptical forms of mature galaxies. They're undergoing violent mergers and collisions at much higher rates. These are galaxies caught in the act of formation, of assembly, of growth. As we look at closer galaxies, galaxies at intermediate distances, seen when the universe was 5 billion years old, 8 billion years old, 10 billion years old, we watch structure emerge over cosmic time. We see spiral arms forming gradually. We see galaxies settling into stable configurations through mergers. We see star formation rates declining as available gas is consumed. This is galactic evolution visible across 13 billion years of cosmic history. The universe isn't static. It has a childhood, an adolescence, an adulthood. Galaxies are born small and chaotic. They grow through mergers and accretion. They mature into stable structures. Eventually they'll die, their star formation exhausted, fading into dimness over trillions of years. And this evolution matches Big Bang predictions precisely. Structure forms hierarchically, small things first, larger things later, through bottom-up assembly driven by gravity. The Hubble Space Telescope gave us this cosmic history book. The James Webb Space Telescope, which we'll discuss later, is now reading even earlier chapters, and finding some surprising plot twists. Here's a subtle but powerful confirmation that's almost philosophical in its implications. Time itself behaves differently across cosmic distances, exactly as relativity and Big Bang cosmology predict. In the 1990s, two competing teams were racing to measure the expansion history of the universe using Type Ia supernovae, exploding white dwarf stars that serve as excellent, standard candles for measuring cosmic distances. Type Ia supernovae are remarkably consistent. They occur when a white dwarf star in a binary system accretes matter from a companion until it reaches the Chandrasekhar limit, 1.4 times the mass of the Sun, at which point carbon fusion ignites explosively, obliterating the star in a thermonuclear detonation. Because they always explode at the same mass, they always have approximately the same intrinsic brightness, about 5 billion times brighter than the Sun at peak. By measuring how bright they appear from Earth, astronomers can calculate how far away they are using the inverse square law. Brightness decreases with the square of distance. But the teams, the Supernova Cosmology Project led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team led by Brian Schmidt in Australia and Adam Rees at Johns Hopkins, noticed something peculiar beyond their expected results about expansion, which we'll discuss shortly. Distant supernovae didn't just look fainter than expected. Their light curves, the graphs showing how brightness changes over time, were stretched out, as if time itself were running in slow motion. A typical Type Ia supernova reaches peak brightness in about 19 days, then fades over the following weeks with a characteristic decay pattern. But supernovae at high redshift, at great distances, showed light curves lasting 25, 30, even 40 days for the same physical process. This is time dilation, a direct consequence of general relativity. The expansion of space doesn't just stretch light waves, causing redshift, it stretches time itself. Events in the distant universe literally unfold more slowly from our perspective because space-time itself is expanding. The amount of observed time dilation matches theoretical predictions with extraordinary precision. A supernova at redshift z equals 0.5, when the universe was about 2/3 its current age, shows a time dilation factor of 1.5, everything happens 1.5 times slower. At redshift z equals 1, when the universe was half its current age, the factor is exactly 2.0, everything happens in slow motion at half speed. This isn't an artifact or illusion. It's direct observational evidence that spacetime itself is dynamic, evolving, expanding, exactly as Big Bang cosmology requires. Remember those sound waves propagating through the early universe, creating the pattern we see in the CMB? They left another signature that astronomers discovered relatively recently, a signature in the distribution of galaxies themselves. The sound waves in the primordial plasma traveled at about 60% the speed of light. In the 380,000 years before recombination, these waves could travel a maximum distance of about 500,000 light-years, the sound horizon, at recombination. When recombination occurred and the universe became transparent, these acoustic oscillations stopped propagating. But their effect on matter distribution persisted. Regions separated by the sound horizon distance had slightly correlated densities. They were slightly more likely to form galaxies at that characteristic separation. In 2005, two teams independently detected this baryon acoustic oscillation, BAO, signal in the distribution of galaxies. When you measure the distances between hundreds of thousands of galaxies, you find a slight excess probability of finding galaxy pairs separated by about 500 million light-years, accounting for cosmic expansion over 13.8 billion years. This is extraordinary. A feature imprinted at 380,000 years is still visible 13.8 billion years later in how galaxies are distributed. The BAO scale acts as a standard ruler, a known distance that appears in the galaxy distribution at different cosmic epochs. By measuring how this scale appears at different redshifts, astronomers can trace the expansion history of the universe over the past 10 billion years. Large galaxy surveys like SDSS-3's BOSS, Baryon Oscillation Spectroscopic Survey, and SDSS-4's EBOSS have measured the BAO signal with exquisite precision, providing yet another independent confirmation of Big Bang cosmology and allowing detailed measurements of cosmic expansion. 6 independent lines of evidence, discovered by different scientists, using different methods, in different decades. Element abundances from nuclear physics. CMB temperature patterns from microwave observations. Galaxy distributions from redshift surveys. Galaxy evolution from deep imaging. Time dilation from supernova light curves. Acoustic oscillations from statistical analysis. All of them converge on the same story, a universe born 13.8 billion years ago in a hot, dense state, expanding and cooling, forming structure through gravity. The case seems overwhelming. But this is only part of the story. The evidence grows stranger, more mysterious, and more deeply troubling the deeper we look into the details. By the late 1990s, cosmology had achieved something remarkable: consensus. Multiple independent observations all pointed to the same model: a universe born in the Big Bang, expanding according to general relativity, forming structure through gravitational collapse. The Big Bang theory had moved from controversial hypothesis to established scientific framework. Cosmologists were confident enough to declare the field was entering a precision era, where the big questions were answered and only details remained to be refined. Some even spoke of cosmology becoming a mature science, like thermodynamics or electromagnetism, well understood, largely complete. Then came 1998, the year two independent teams made a discovery so shocking, so completely unexpected, that it forced physicists to confront the uncomfortable reality that we understand less than 5% of the universe. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team, led by Brian Schmidt at Australian National University and Adam Rees at the Space Telescope Science Institute, were engaged in friendly but intense competition throughout the 1990s. Both teams had the same goal: use Type Ia supernovae as cosmic distance markers to measure how the expansion rate of the universe has changed over time. The expectation, shared by virtually every cosmologist, was that expansion must be slowing down, decelerated by gravity. Think about it. The Big Bang sent everything flying outward. Gravity pulls everything inward. Therefore, gravity must be slowing the expansion, like gravity slowing a ball thrown upward. The only question was how much slowdown, enough to eventually halt expansion and cause recollapse, a closed universe, or insufficient to stop expansion, leading to eternal expansion at an ever slower rate, an open universe. Both teams searched for distant Type Ia supernovae, standardizable cosmic explosions bright enough to see across billions of light-years. They measured distances to these supernovae using their brightness, and velocities using their redshifts. By comparing distance and velocity, they could determine whether expansion was slowing down, and by how much. Between 1995 and 1998, both teams observed dozens of distant supernovae, carefully analyzed the data, checked for systematic errors, and independently reached their conclusions. In early 1998, both teams prepared to announce their results. Both expected to report deceleration. Both expected to measure how much the expansion was slowing. Instead, both found the same shocking result: the expansion isn't slowing down at all. It's speeding up. Distant supernovae were systematically fainter than expected, too faint by about 25%. That means they're farther away than they should be if expansion were decelerating. The only way to explain this is if space is expanding faster now than it was billions of years ago. The expansion is accelerating. Adam Rees later recalled, "My first thought was that we'd screwed up somewhere." Brian Schmidt remembered thinking there must be a systematic error in the data. Saul Perlmutter's team spent months checking and rechecking everything, convinced they'd made a mistake. But both teams found the same thing. The result was robust. Distant supernovae are definitely too faint. The expansion is definitely accelerating. This shouldn't be possible. Gravity attracts. It pulls things together. What force could possibly overpower the combined gravitational pull of every galaxy, every star, every particle in the entire observable universe? Hundreds of billions of galaxies, each containing hundreds of billions of stars. In February 1998, Perlmutter's team announced their results at a meeting in California. The audience was stunned. Many were skeptical. Some suggested systematic errors. Others wondered if Type Ia supernovae might not be standard candles after all. Maybe their intrinsic brightness evolves over cosmic time. But then Schmidt and Rees announced their independent results just weeks later. Two teams, different telescopes, different analysis methods, same conclusion: acceleration. The discovery was so unexpected, so revolutionary, that it took months for the physics community to accept it. In 1998, both teams published their results in top journals. Over the following years, more observations confirmed the result beyond doubt. In 2011, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics for the discovery of the accelerating expansion of the universe through observations of distant supernovae. But winning a Nobel Prize didn't solve the fundamental mystery. What's causing the acceleration? Scientists call it dark energy, a deliberately vague name for something we fundamentally don't understand. It's not dark in the sense of being shadowy or hidden. It's dark because we have absolutely no idea what it is. It's an admission of ignorance packaged as a label. Current observations suggest dark energy comprises roughly 68% of the total energy content of the universe. It's the dominant component, the single largest contributor to what the universe is made of. Yet we don't know what it is. Add in dark matter, the mysterious substance that provides extra gravity to hold galaxies together, first detected by Vera Rubin and others in the 1970s through galaxy rotation curves, and you get another 27% of the universe's content. That means normal matter, baryonic matter, the protons, neutrons, and electrons that make up atoms, that compose stars and planets and trees and human bodies, accounts for less than 5% of the universe. Think about that. 95% of the universe is completely mysterious. We don't know what dark energy is. We don't know what dark matter is. We can only detect them through their gravitational effects. Dark matter through its extra gravity holding galaxies together. Dark energy through its anti-gravitational effect accelerating cosmic expansion. The leading theoretical explanation for dark energy is Einstein's cosmological constant, the lambda term that Einstein added to his equations in 1917 to maintain a static universe, which he later reportedly called his greatest blunder when Hubble discovered expansion. Ironically, Einstein might have been right after all, just for completely different reasons than he intended. The cosmological constant represents the energy density of empty space itself, vacuum energy. According to quantum field theory, even completely empty space isn't truly empty. It's seething with quantum fluctuations, virtual particle-antiparticle pairs constantly popping into existence and annihilating in tiny fractions of a second. These quantum fluctuations should contribute energy to the vacuum. The problem, and this is one of the most embarrassing problems in all of physics, is that when physicists calculate how much vacuum energy there should be based on quantum field theory, they get an answer that's 10 to the power of 120 times larger than what we observe. That's not a typo. Not 10 times too large. Not 1,000 times. Not 1,000,000 times. 10 to the power of 120 times, a 1 followed by 120 zeros, larger than observed. This is called the cosmological constant problem, and it's arguably the worst theoretical prediction in the entire history of physics, off by 120 orders of magnitude. It's like predicting someone's height as 10 to the power of 120 meters when they're actually 1.7 meters tall. It's like predicting a grain of sand weighs as much as 10 to the power of 120 universes. Why is the vacuum energy so incredibly small compared to what quantum theory predicts? Nobody knows. There's no accepted explanation. It's a complete mystery. Some physicists propose alternative explanations. Maybe dark energy isn't constant but varies over time, called quintessence, after the fifth element of ancient philosophy. Maybe it's connected to extra dimensions of space. Maybe it's a sign that general relativity needs modification on cosmic scales. Maybe we're completely wrong about something fundamental. But whatever dark energy is, its existence tells us something profound. The Big Bang didn't just create matter and radiation. It created something else. Something dominant, something mysterious, something that determines the ultimate fate of the universe. Let's turn to another deep mystery hidden in plain sight within the cosmic microwave background, a problem so severe that it suggests standard Big Bang cosmology is incomplete. The CMB has almost exactly the same temperature in every direction, 2.725 Kelvin, with tiny fluctuations of only 1 part in 100,000. On large scales, the universe is remarkably, even suspiciously, uniform. But there's a profound problem. Regions on opposite sides of the sky are so far apart that light couldn't have traveled between them since the Big Bang. They've never been in causal contact, never exchanged information, energy, or any kind of influence. Let's do the math carefully. The observable universe, the maximum distance we can see in any direction, extends about 46.5 billion light-years from Earth. That's not 13.8 billion light-years, the age of the universe times the speed of light, because space itself has been expanding while light travels through it. When we look at the CMB, we're seeing light that left regions 46.5 billion light-years away when the universe was 380,000 years old. If we look in the opposite direction, we see light from a region also 46.5 billion light-years away, meaning those two regions are now separated by about 93 billion light-years. But, and here's the crucial point, those regions have never been in causal contact. Even traveling at light speed since the Big Bang, signals from one region couldn't have reached the other. They're beyond each other's cosmic horizons, causally disconnected, like ships in different oceans that have never communicated and never could. So why are they the same temperature to 1 part in 100,000? Temperature uniformity requires thermal equilibrium, energy exchange that equalizes temperatures. Hot coffee and cold milk, poured together, reach a uniform temperature through molecular collisions that transfer heat. But these cosmic regions couldn't have exchanged heat. They've never touched, never communicated, never influenced each other in any way. Imagine conducting an experiment. Place two identical thermoses of coffee on opposite ends of a football field. Completely isolate them from each other and from any external heat source. Wait 24 hours. Then open both simultaneously and measure their temperatures. 67.324 degrees Celsius in one, 67.324 degrees Celsius in the other. Exactly the same to 3 decimal places. This would be extraordinary, impossible through normal physics. How could two isolated systems reach precisely the same temperature without ever interacting? Yet the cosmic microwave background shows this impossible uniformity across the entire sky. Regions that have never been in causal contact somehow have exactly the same temperature. This is the horizon problem. Standard Big Bang cosmology predicts these regions should have random, uncorrelated temperatures. Instead, they're in perfect thermal equilibrium, as if they were once in contact but couldn't have been according to the timeline. Something is deeply wrong, either with our understanding of the early universe or with the standard Big Bang timeline itself. Here's another mystery embedded in the fabric of space-time itself. The geometry of the universe depends on its total energy density. Einstein's general relativity predicts 3 possibilities. Positive curvature, closed universe. If the total energy density is above a critical value, space curves back on itself like the surface of a sphere. Parallel lines eventually converge. Travel far enough in a straight line, and you'd eventually return to your starting point from the opposite direction. Such a universe would eventually stop expanding and recollapse in a big crunch. Negative curvature, open universe. If the energy density is below the critical value, space curves outward like a saddle or a Pringle potato chip. Parallel lines diverge. Such a universe expands forever, cooling toward absolute zero. Flat, critical density. If the energy density equals exactly the critical value, about 5 atoms of hydrogen per cubic meter, space is geometrically flat on cosmic scales. Parallel lines remain parallel forever, Euclidean geometry holds, and the expansion eventually coasts to a halt in the infinite future. Measurements from the WMAP and Planck satellites show the universe is flat. The spatial curvature is 0 to within 0.4% measurement error. Space, on the largest scales, is Euclidean. The geometry you learned in high school applies to the cosmos. But here's the profound problem. Flatness is incredibly unstable in standard Big Bang cosmology. Think of it this way. Imagine balancing a pencil on its tip. Perfectly vertical is a state of zero angular deviation, flat in the angular sense. But the slightest disturbance will cause it to fall. The vertical position is unstable. Similarly, the flat universe represents an unstable equilibrium in cosmology. Any deviation from perfect flatness gets amplified exponentially by cosmic expansion. If the density at 1 second after the Big Bang differed from the critical value by even 1 part in 10 to the power of 15, the universe today would be obviously curved, either collapsed long ago or so dispersed that no structure could form. For the universe to be flat today, the density at 1 second after the Big Bang must have been fine-tuned to the critical value to 1 part in 10 to the power of 15. At the Planck time, 10 to the power of -43 seconds, the fine-tuning must have been 1 part in 10 to the power of 60. That's like balancing the pencil to 1 part in 10 to the power of 60, needing to align it vertically to an accuracy of 10 to the power of -60 degrees, a trillion times more precise than the width of a proton. Why is the universe so precisely balanced? Why is the density so incredibly close to the critical value? This is the flatness problem. It's not impossible for the universe to be flat, but it requires extraordinarily precise initial conditions that seem fantastically improbable without some underlying explanation. Remember Big Bang nucleosynthesis, the nuclear physics of the first 20 minutes that predicted element abundances with stunning accuracy. Hydrogen, perfect match. Helium, 4, perfect match. Deuterium, perfect match. Helium, 3, perfect match. But lithium, 7 is wrong. Theoretical calculations based on Big Bang nucleosynthesis, using well-understood nuclear physics and measured cosmological parameters from the CMB, predict the universe should contain about 3 times more lithium-7 than we actually observe in the oldest stars. This isn't a small discrepancy. It's a factor of 300%. That's huge in precision cosmology, where other predictions match to within a few percent. Astronomers have measured lithium abundances in hundreds of old, metal-poor stars formed from nearly pristine primordial gas. These measurements are consistent. Lithium-7 abundance is about 1.6 times 10 to the power of -10 relative to hydrogen. But theory predicts about 5 times 10 to the power of -10. Where did the lithium go? Scientists have explored numerous explanations. Maybe stars destroyed some lithium through internal processes, mixing surface gas down to hot interiors where lithium burns. But detailed stellar evolution models show this can't account for a factor of 3. Maybe our measurements are wrong. Spectroscopic analysis is tricky. But hundreds of independent observations from different telescopes all show the same deficit. Maybe the nuclear physics is wrong. Maybe the reaction rates for lithium-7 production in the early universe are inaccurate. But these rates have been measured in laboratories and checked against other astrophysical processes. They appear solid. Maybe there's new physics in the early universe, exotic particles or processes not in the standard model. But inventing new physics to fix one problem risks creating other problems elsewhere. The lithium problem remains unsolved after decades of research. It's a genuine anomaly, the first real crack in the foundation of Big Bang nucleosynthesis. Either our understanding of stellar evolution is incomplete in ways we don't recognize, or something happened in the early universe that destroyed lithium, something not accounted for in standard Big Bang theory. Dark matter simulations predict that large galaxies like the Milky Way should be surrounded by thousands of small satellite galaxies, dwarf galaxies containing millions to billions of stars orbiting in the gravitational field of the larger galaxy. But we only observe a few dozen satellite galaxies around the Milky Way. The large and small Magellanic Clouds are the most prominent, visible to the naked eye from southern latitudes. But simulations predict hundreds or thousands of satellites, not dozens. Where are they? Did they never form? Were they destroyed? Are they there but too dim to detect? Or is our model of dark matter wrong? This is the missing satellites problem, and it suggests either that galaxy formation physics is more complex than we understand, or that dark matter doesn't behave exactly as our simplest models predict. Here's a more recent and deeply troubling problem that's currently causing significant anxiety in cosmology. The Hubble constant, the current expansion rate of the universe, can be measured in 2 completely independent ways. Local measurements. Observe nearby objects like Cepheid variable stars and Type Ia supernovae to build a cosmic distance ladder and measure the expansion rate directly. Adam Rees and his team have done this with extraordinary precision using Hubble Space Telescope data. They find h equals 73.0 plus or minus 1.0 km/s/mpc. Early universe measurements. Analyze the cosmic microwave background using Planck's satellite data, input the measurements into the standard cosmological model, called lambda-CDM, and calculate what the expansion rate should be today. This method gives h equals 67.4 plus or minus 0.5 kilometers per second per mpc. These two numbers don't agree. The discrepancy is about 9%, small in everyday terms, but huge in cosmology where both measurements have error bars of less than 2%. This isn't a measurement error. Both teams have checked and rechecked everything. The local measurements have been confirmed by independent methods using red giant stars and other distance indicators. The CMB measurements have been verified by other CMB experiments. The discrepancy is real, and it's statistically significant at more than 5 sigma, meaning there's less than 1 in a million chance it's a random fluctuation. Something is wrong. Either there's an unrecognized systematic error in one or both measurements, but what? The standard cosmological model, lambda-CDM, is incomplete or wrong. There's new physics between the CMB era and today. Maybe dark energy evolves over time, or there are additional particle species, or something stranger. This Hubble tension is currently one of the hottest topics in cosmology. It might be pointing to a genuine crisis, a sign that our understanding of cosmic expansion is incomplete. The evidence extends beyond simple confirmation into the realm of genuine mystery and paradox. Each answer generates new questions. Each solution reveals new problems hidden beneath. Dark energy dominates the universe, but we don't know what it is. The universe is suspiciously uniform despite never being in causal contact. It's flat to extraordinary precision despite flatness being unstable. Lithium abundances don't match predictions. Expansion rate measurements don't agree. And the James Webb Space Telescope has just added another mystery to the pile, one that threatens to overturn our understanding of how galaxies form. Faced with the horizon problem, the flatness problem, and other deep mysteries of the early universe, physicists realized that standard Big Bang cosmology, despite its successes, must be incomplete. Something crucial was missing from the story. In 1980, a young physicist at MIT named Alan Guth proposed something radical, something that sounded like science fiction: cosmic inflation. Guth's idea was audacious. In the first incomprehensibly brief instant after the Big Bang, between about 10 to the power of -36 and 10 to the power of -32 seconds, the universe underwent a period of exponential expansion far more rapid than normal cosmic expansion. During inflation, space didn't just expand, it doubled in size every 10 to the power of -37 seconds or so. That means in less than 10 to the power of -32 seconds, a region smaller than a proton inflated to larger than a galaxy, perhaps even larger than the entire observable universe today. Think about exponential growth. If you start with 1 penny and double it every day, 1 cent, 2 cents, 4 cents, 8 cents, after 30 days you'd have $5.3 million. After just 11 more days, over $10 billion. Exponential growth is staggeringly powerful. Cosmic inflation was like that, but far more extreme. In a tiny fraction of a second, a microscopic patch of space expanded by a factor of perhaps 10 to the power of 30 or more, inflating by 30 orders of magnitude, a billion times larger. This solves the horizon problem elegantly. Those regions we see on opposite sides of the CMB were once close together, close enough to be in thermal contact and reach equilibrium. Then inflation stretched them apart to opposite sides of the observable universe. It's like drawing two dots very close together on a deflated balloon. The dots can communicate, they're in contact. Then you inflate the balloon explosively. Now the dots are on opposite sides, far apart, but they were once together. That's why they have the same temperature. Inflation also solves the flatness problem. Exponential expansion stretches space so dramatically that any initial curvature becomes negligible. Imagine the surface of a sphere. On small scales, it's obviously curved. But inflate it to cosmic proportions, and locally it appears flat, just as the Earth's surface appears flat when you're standing on it, even though the Earth is a sphere. Inflate space by a factor of 10 to the power of 30, and any initial curvature gets stretched to imperceptibility. The universe becomes geometrically flat not because of fine-tuned initial conditions, but because inflation automatically flattens space. But here's the profound part. Inflation also explains where the CMB fluctuations came from, those 1 part in 100,000 temperature variations that seeded all cosmic structure. During inflation, quantum fluctuations, tiny, random variations in the energy field driving inflation, got amplified to cosmic scales. Microscopic quantum uncertainties in the inflaton field, the hypothetical field causing inflation, were stretched by inflation into macroscopic density perturbations. These quantum fluctuations, magnified to astronomical sizes, became the seeds of galaxies. The pattern of these fluctuations depends on the details of the inflation process, and remarkably, the predicted pattern matches the observed CMB pattern extraordinarily well. Inflation is elegant, powerful, and explains multiple mysteries with one mechanism. It's one of the most successful theoretical ideas in cosmology. But, and this is crucial, inflation isn't proven. It's a hypothesis, an extraordinarily well-motivated and successful hypothesis, but still speculative. We don't know for certain that inflation happened. We don't know what caused it. We don't know what the inflaton field is, it doesn't correspond to any known particle or force. We don't know what stopped inflation. Scientists at institutions like MIT, Stanford, Princeton, Caltech, the European Space Agency, and NASA are working to test inflation observationally. The key signature would be primordial gravitational waves, ripples in spacetime itself created by inflation, which would leave a distinctive imprint on the polarization of the CMB. In March 2014, the BICEP-2 experiment at the South Pole announced the detection of this signature, what cosmologist John Kovac called smoking gun evidence for inflation. The physics community erupted with excitement. Media proclaimed it potentially the greatest discovery in cosmology since the CMB itself. Then came the deflation. Within months, further analysis showed the signal was contaminated by dust in our own galaxy. Tiny particles of silicates and carbon floating in interstellar space, also creating polarized microwave emission that mimicked the inflation signature. The search continues. Experiments like BICEP-3, the Keck Array, the Simons Observatory, and the proposed CMB-S4 project are pushing to higher sensitivity, trying to detect or rule out inflation's gravitational wave signature. Despite overwhelming evidence, not everyone accepts standard Big Bang cosmology. Some physicists propose alternatives, each trying to solve different problems. The steady-state theory, proposed in 1948 by Fred Hoyle, Thomas Gold, and Hermann Bondi, this theory suggested the universe is eternal and unchanging on cosmic scales, with new matter continuously created to maintain constant density as space expands. The perfect cosmological principle held that the universe looks the same at all times and places. Fred Hoyle championed this idea passionately, becoming the Big Bang's most eloquent opponent. But the discovery of the CMB in 1965 dealt a fatal blow. Steady state couldn't explain the cosmic microwave background. The theory is now considered defunct, though Hoyle never fully accepted the Big Bang even before his death in 2001. Cyclic and bouncing models. These propose that the universe undergoes endless cycles of expansion and contraction. Each Big Bang is actually a big bounce. The universe contracts in a big crunch, then rebounds in a new expansion phase. Roger Penrose's conformal cyclic cosmology is a modern, sophisticated variant. Penrose, who won the 2020 Nobel Prize for black hole physics, proposes that the universe goes through infinite eons, each beginning with something resembling a Big Bang and ending in an era of maximum expansion and heat death, which somehow transitions into the next aeon. Paul Steinhardt and Neil Turok have developed ekpyrotic models involving collisions between higher-dimensional objects called branes. These models attempt to explain fine-tuning and flatness without inflation. Plasma cosmology, proposed by Nobel laureate Hannes Alfvén, this theory suggests electromagnetic forces, not gravity, shaped large-scale cosmic structure. But it can't explain the CMB, element abundances, or observed galaxy distributions. It's largely rejected by the mainstream. Eternal inflation and the multiverse. Perhaps the most radical extension of inflation suggests that inflation never fully stops. In most of space, inflation continues eternally, but in some regions, including ours, it ends, creating a bubble universe. In this scenario, our observable universe is just one bubble in an eternally inflating megaverse. Other bubbles exist beyond our cosmic horizon, potentially with different physical laws, different constants of nature, even different numbers of dimensions. This leads to the multiverse hypothesis. We're not in the universe, but a universe, one of countless, perhaps infinite universes where every possible combination of physical laws exists somewhere. The multiverse is controversial. Some physicists embrace it as the natural consequence of inflation and quantum mechanics. Others reject it as untestable metaphysics, not science. If other universes are forever beyond our observation, can we call it science? These alternative theories force us to reconsider fundamental assumptions about existence itself. Is the Big Bang the ultimate beginning, or just a transition between previous and future states? Is time eternal, stretching infinitely into past and future? Is our universe unique with its specific laws of physics, or just one random sample from an infinite ensemble? The evidence points strongly to some version of the Big Bang, a hot, dense beginning followed by expansion. But the details remain contested, the ultimate origin unclear, the larger context unknown. The James Webb Space Telescope, launched on Christmas Day 2021 and activated in mid-2022, represents a quantum leap in observational capability. With a mere 6.5 meters across, nearly 3 times larger than Hubble, and sensitivity to infrared light, JWST can peer deeper into cosmic history than any previous instrument. And what it's finding is both confirming and challenging our models in ways that have cosmologists buzzing with excitement and a bit of anxiety. In July 2022, just weeks after JWST began science operations, astronomers released stunning images of galaxies at unprecedented distances. Within months, they found galaxies at redshifts of 12, 13, even possibly 16 or higher, meaning we're seeing them as they appeared just 200 to 400 million years after the Big Bang. According to standard models of galaxy formation, early galaxies should be small, chaotic, irregular, protogalaxies still assembling from primordial gas clouds through violent, turbulent processes. Star formation should just be beginning. Structures should be disordered. Instead, JWST found massive, structured galaxies containing a billion stars or more, some showing well-defined spiral arms, others appearing as mature elliptical galaxies. They're far too evolved for their age, like finding a fully grown adult human just months after conception. One particularly troubling galaxy, designated CEERS 93316, appeared at redshift 16.7, just 250 million years after the Big Bang, yet contained as much mass as the modern Milky Way. Astronomers are struggling to explain this. How could galaxies assemble so quickly? Did the first stars form earlier than we thought? Does dark matter behave differently than assumed? Are our models of star formation and galaxy evolution fundamentally incomplete? Or, and this is the truly unsettling possibility, could the universe be older than 13.8 billion years? Some researchers have even suggested, half-jokingly, that maybe the Big Bang didn't happen exactly as we thought. But that's almost certainly too radical. There's too much other evidence supporting the Big Bang timeline. The most likely explanation is that our models of early galaxy formation are wrong or incomplete. Perhaps star formation was more efficient in the early universe than simulations predict. Perhaps the first stars were more massive than later generations, forming faster and brightening galaxies more quickly. Perhaps feedback processes that regulate star formation operated differently. JWST observations are forcing a major revision of galaxy formation theory, not overturning the Big Bang, but requiring significant modifications to how we think structure assembled in the first billion years. This is science in action. Observations challenging models, forcing refinement and deeper understanding. The next 2 decades promise revolutionary advances in cosmology, with multiple missions and telescopes designed to probe the universe's deepest mysteries. The Vera C. Rubin Observatory, formerly the Large Synoptic Survey Telescope, beginning operations in Chile in 2025, will survey the entire visible sky every few nights using an 8.4-meter telescope with the world's largest digital camera, 3.2 billion pixels. Over 10 years, it will map billions of galaxies, track supernovae and variable stars, search for dark matter, and measure cosmic acceleration with unprecedented precision. The Nancy Grace Roman Space Telescope, NASA's next flagship observatory launching in May 2027, will conduct wide-field infrared surveys covering areas 100 times larger than Hubble. Its primary goals include mapping dark energy's evolution over cosmic history and conducting microlensing surveys to find exoplanets. The LISA mission, Laser Interferometer Space Antenna, an ESA-NASA collaboration planned for launch in the mid-2030s, will detect gravitational waves from space. Unlike ground-based detectors like LIGO that detect waves from merging black holes and neutron stars, LISA will be sensitive to much lower frequencies, gravitational waves from supermassive black hole mergers, and potentially primordial gravitational waves from cosmic inflation. If LISA detects inflation's gravitational wave signature, it would confirm one of the most profound predictions in cosmology and open a window into the first instance of the universe's existence. Ground-based CMB experiments. The Simons Observatory in Chile, CMB-S4, a next-generation array of telescopes at the South Pole in Chile, and other projects will map the cosmic microwave background with exquisite precision, searching for inflation signatures and measuring cosmological parameters to fractions of a percent. The Square Kilometre Array, SKA, under construction in Australia and South Africa, SKA will be the world's largest radio telescope, sensitive enough to detect neutral hydrogen from the first galaxies during the cosmic dark ages, the era between recombination at 380,000 years and the formation of the first stars at perhaps 100 million years. Recent technological and theoretical advances suggest we're entering a new golden age of cosmology. Machine learning and AI are finding patterns in cosmic data that human analysts miss. Neural networks trained on simulations can identify galaxy mergers, measure dark matter distributions, and classify cosmic structures with superhuman accuracy. Quantum computer simulations are beginning to model the early universe with greater fidelity, potentially solving computational problems intractable for classical computers, like following the evolution of quantum fluctuations during inflation. Gravitational wave astronomy, LIGO, Virgo, and CAGRA detectors have opened an entirely new window into the universe, detecting dozens of black hole and neutron star mergers. Future detectors like Einstein Telescope and Cosmic Explorer will be 10 to 100 times more sensitive, potentially detecting gravitational waves from the early universe. Multi-messenger astronomy, combining electromagnetic observations, gravitational waves, and neutrino detections, provides multiple independent views of cosmic events. The 2017 neutron star merger GW 170817 was observed in gravitational waves, gamma rays, X-rays, visible light, and radio waves, providing unprecedented insights into nuclear physics, gravity, and cosmology. Within the next decade, we may answer questions that seemed forever beyond reach. What happened in the first trillionth of a second after the Big Bang? Did cosmic inflation actually occur? And if so, what caused it? What is dark energy? Is it constant, or does it evolve over time? What is dark matter? Is it a new type of particle, or does it represent a modification of gravity? Are there other universes beyond our cosmic horizon? How did the first stars and galaxies form? The implications are staggering and mind-bending. If inflation is real, our observable universe, 93 billion light-years across, containing hundreds of billions of galaxies, may be an infinitesimal fraction of a vastly larger cosmos. Everything we can see, every galaxy observed by every telescope, might occupy less volume in the total universe than a single atom occupies in the Earth. If the universe is cyclic, time itself may have no beginning or end. The Big Bang would be a bounce, a transformation, a transition, not creation ex nihilo, but recycling of a previous cosmic state. Time extends infinitely into past and future, with our Big Bang just one episode in an eternal cosmic drama. If we're part of a multiverse generated by eternal inflation, the fundamental constants of nature, the strength of gravity, the mass of the electron, the cosmological constant, the speed of light, may be random accidents of our particular bubble. In other regions of the multiverse, different values prevail, creating universes where stars can't form, where atoms are unstable, where life is impossible. We might be privileged not in being at the center of the universe, but in existing in a rare bubble where the constants happen to allow complexity, structure, and consciousness to emerge. Or perhaps, and this is both exciting and unsettling, the universe is far stranger than any of our current theories imagine. Maybe there are aspects of reality so foreign to human experience that we don't even have the conceptual categories to think about them yet. 500 years ago, humans couldn't have imagined black holes, quantum entanglement, or cosmic inflation. What might we be unable to imagine now that future physics will reveal? The universe may be stranger than we can suppose. Not just stranger than we do suppose, but stranger than we can suppose given our evolved human cognition. The evidence points to a cosmos far more mysterious, far more profound, and far more deeply strange than anyone imagined when Hubble first detected cosmic expansion in 1929. So we return to the question we began with. Is the Big Bang theory true? The answer is simultaneously simple and profound, satisfying and frustrating, clear and deeply ambiguous. The Big Bang theory, the framework describing a universe born 13.8 billion years ago in a hot, dense state, expanding and cooling ever since, is the best explanation we have for the observable universe. It's supported by multiple independent lines of evidence that would be impossible to explain otherwise, cosmic expansion, the cosmic microwave background, light element abundances, galaxy evolution, large-scale structure, time dilation in distant supernovae, baryon acoustic oscillations. No other theory explains all these phenomena. The evidence is overwhelming, not perfect, not without puzzles, but overwhelming nonetheless. But best available explanation doesn't mean complete, final truth. It means this is where science currently stands, based on observations and reasoning, subject to revision if new evidence emerges. The most profound implications emerge when we consider what the Big Bang Theory doesn't answer. The deepest, most philosophically challenging questions that may sit at the boundary between physics and metaphysics. What caused the Big Bang itself? This is perhaps the ultimate question, and current physics cannot answer it. The laws of physics as we understand them break down at the singularity. General relativity predicts infinite density, infinite temperature, infinite spacetime curvature, mathematical infinities that signal not reality, but the theory's own limitation, its domain of validity ending. At the singularity, spacetime curvature becomes so extreme that quantum effects become important. But we don't have a theory of quantum gravity, a framework that successfully unifies general relativity's description of spacetime with quantum mechanics' description of matter and energy at the smallest scales. String theory offers possibilities. Perhaps the Big Bang emerged from the collapse of a previous universe, or from quantum tunneling in a pre-existing space, or from collision between higher dimensional membranes. But string theory remains unproven, its predictions untested, its status controversial. Loop quantum gravity suggests the Big Bang might be a big bounce, the universe contracting to a minimum, but not zero, size, then rebounding into expansion. Quantum effects prevent the singularity, like a quantum trampoline bouncing the universe back from collapse. Or perhaps, as Stephen Hawking proposed, time itself didn't exist before the Big Bang. Asking what came before makes no sense, like asking what's north of the North Pole. Time is a dimension of spacetime. If spacetime began at the Big Bang, there is no before, no prior state, no cause in the usual sense. But this feels like evading the question rather than answering it. Why does spacetime exist at all? Why these laws of physics rather than different ones or none? Why something rather than nothing? The universe appears remarkably fine-tuned for the existence of structure, complexity, and life. Change any of several fundamental constants even slightly, and the universe becomes sterile, incapable of producing stars, planets, chemistry, or any complexity beyond primordial hydrogen. Consider just a few examples. The cosmological constant, dark energy. If it were slightly larger, space would expand so rapidly that galaxies couldn't form. Matter would be pulled apart before gravity could collect it into structures. If it were slightly smaller in the opposite direction, actually negative, the universe would have collapsed in a big crunch long before stars could evolve. The observed value appears fine-tuned to about 1 part in 10 to the power of 120. The worst fine-tuning problem in physics. The strength of gravity. If gravity were slightly stronger, by a factor of 3,000, stars would burn through their fuel in a year rather than billions of years. Too fast for planets to form or life to evolve. If gravity were slightly weaker, stars couldn't ignite nuclear fusion, they'd be cold, dark balls of hydrogen. The electromagnetic force. If it were 4% stronger, carbon-12, essential for organic chemistry, couldn't form in stars. If it were different by similar amounts in other directions, molecules couldn't form. Chemistry itself would be impossible. The strong nuclear force. If it were 0.5% stronger, all hydrogen would have been converted to helium in the Big Bang. No water, no stars burning through hydrogen fusion. If it were 0.5% weaker, atomic nuclei beyond hydrogen couldn't exist. The universe would contain only the simplest element. The neutron-proton mass difference. Neutrons are 0.1% heavier than protons. If this difference were larger or smaller by about 1%, either all protons would decay into neutrons or all neutrons into protons. Either way, atoms couldn't exist. The ratio of electrons to protons. They're equal in number to 1 part in 10 to the power of 37 or better. If this weren't so, electromagnetic forces would dominate gravity, preventing galaxy and star formation. Timestamp 58:00. These aren't just rough requirements, they're precise, multiple, independent constraints. The universe sits in a narrow, habitable zone, in parameter space, a tiny island of life-permitting conditions in an ocean of sterile possibilities. Why? 3 types of answers have been proposed. 1. Design. The universe was deliberately created with these parameters by an intelligent agent, God, a cosmic engineer, a simulator running our universe as a computation. This is the theological or simulation hypothesis answer. Most scientists are uncomfortable with this because it explains one mystery, fine-tuning, by invoking a bigger mystery, an intelligent designer, and it's not scientifically testable. But the fine-tuning is so striking that even some atheist physicists acknowledge it as philosophically puzzling. 2. Necessity. Perhaps the constants couldn't have been different. Some deeper theory we haven't discovered yet explains why these are the only possible values. Maybe there's only one mathematically consistent universe, and we're living in it. This would be elegant, but we have no evidence for it. As far as we can tell, the constants could have other values. We can write down perfectly consistent mathematical theories with different constants, they just don't produce interesting universes. 3. Selection. Anthropic principle in a multiverse containing every possible combination of constants. Most universes are sterile. But some, a tiny fraction, happen to have life-permitting constants. We necessarily find ourselves in one of the rare life-permitting universes, because we couldn't exist in the sterile ones to observe them. This is anthropic reasoning. The universe must be compatible with conscious observers, because otherwise there'd be no one to ask, why is the universe life-permitting? It's like a lottery winner asking, why did I win? The answer isn't that they're special, but that millions of people played, and they wouldn't be asking the question if they hadn't won. The anthropic principle is controversial. Some physicists embrace it as the natural consequence of inflation and multiverse cosmology. Others reject it as giving up on finding real explanations, as explaining everything by explaining nothing. With dark energy accelerating cosmic expansion, the universe faces a cold, lonely ending, what cosmologists call the Big Freeze, or heat death. In about 100 billion years, galaxies beyond our local group, the Milky Way, Andromeda, and several dozen smaller galaxies bound together by gravity, will have receded beyond the cosmic horizon. Their light will be redshifted to infinite wavelength. They'll become completely invisible, as if they never existed. Future civilizations, if any exist, will observe a universe containing only their local galaxy, surrounded by darkness. They'll have no evidence of cosmic expansion, no CMB, redshifted into undetectability, no distant galaxies. They'll be unable to discover the Big Bang or cosmic history. The universe will appear static and eternal, as humans once believed. In 1 trillion years, star formation will largely cease as available gas is consumed. Existing stars will exhaust their fuel and die, the smallest red dwarfs lasting longest, eventually fading to cold black dwarfs. In 10 to the power of 14 years, 100 trillion years, the last stars will go dark. In 10 to the power of 20 years, dead stars and planets will be ejected from galaxies or fall into central black holes through gravitational interactions. In 10 to the power of 40 to 10 to the power of 100 years, depending on uncertain physics, even protons might decay, dissolving all remaining matter into radiation. In 10 to the power of 100 years, black holes themselves will evaporate through Hawking radiation, quantum effects causing them to slowly radiate away their mass until they disappear in final flashes. After 10 to the power of 100 years, the universe will contain only a thin soup of photons and other particles, cooling toward absolute zero, approaching a state of maximum entropy, the heat death, and eternal darkness punctuated only by rare, random quantum fluctuations. Unless dark energy changes, unless new physics intervenes, unless the universe is cyclic and bounces into a new Big Bang, unless quantum mechanics allows fluctuations to trigger new universes spontaneously, the ultimate fate remains uncertain. We don't understand dark energy well enough to predict confidently what happens in the far future. But one thing seems clear, the universe of 1 trillion years hence will be vastly different from today. Colder, darker, emptier, more silent. The current epoch, with stars shining and galaxies wheeling through space, is a brief, magnificent moment in an inconceivably long cosmic story. We began this journey with a question that has haunted humanity since we first looked up at the stars and wondered about our origins. Is the Big Bang Theory true? We've traveled through nearly a century of discoveries, from Edwin Hubble's observations at Mount Wilson in 1929 to the James Webb Space Telescope's stunning images in 2022. We've examined the evidence piece by piece, mystery by mystery, paradox by paradox. What we know with extraordinary confidence: the universe is expanding. Every galaxy beyond our local group is receding, with velocity proportional to distance. This expansion isn't motion through space, it's the expansion of space itself, carrying galaxies along. The universe had a hot, dense beginning. The cosmic microwave background, a uniform glow of radiation at 2.725 Kelvin filling all of space, is the cooled remnant of the primordial fireball, a photograph of the universe at 380,000 years old. The universe has evolved over 13.8 billion years. Galaxies at different distances look different because we're seeing them at different ages. Structure has formed hierarchically, small things first, larger things later, through gravitational collapse amplifying tiny initial fluctuations. The lightest elements were forged in the first 20 minutes. The predicted abundances of hydrogen, helium, and deuterium match observations with stunning precision, confirming that nuclear fusion occurred throughout the universe in its earliest moments. Space is geometrically flat. Time dilates across cosmic distances. The large-scale structure matches CMB predictions. Baryon acoustic oscillations appear in galaxy distributions. Every independent line of evidence points to the same conclusion. The case for the Big Bang, for some version of a hot, dense beginning followed by expansion and cooling, is overwhelming. It's not speculation or wishful thinking. It's the best-tested, most confirmed theory in cosmology, supported by observations that would be impossible to explain otherwise. But, and this but, is crucial, the Big Bang Theory is incomplete. What we don't know. We don't know what caused the Big Bang. Was there a before? Did time itself begin, or is the Big Bang a transition from some previous state? Current physics cannot answer. The equations break down at the singularity. We don't know what happened in the first incomprehensibly brief instance. Did cosmic inflation occur? If so, what drove it? What stopped it? The evidence is suggestive but not conclusive. We don't know what dark matter is. It comprises 27% of the universe's content, provides the gravity that holds galaxies together, but we've never directly detected it. Is it a new type of particle? A modification of gravity? Something stranger? We don't know what dark energy is. It comprises 68% of the universe, the dominant component, yet we have no idea what it represents. Is it the energy of empty space? A new force field? Evidence that general relativity needs modification? The cosmological constant problem remains the worst theoretical prediction in physics, off by 120 orders of magnitude. We don't know why the universe is so precisely fine-tuned for life. Change any of dozens of constants even slightly, and complexity becomes impossible. Is this design, necessity, or selection from a multiverse? Each answer is philosophically troubling in different ways. We don't fully understand how the first galaxies formed. JWST's discovery of massive mature galaxies just 300 million years after the Big Bang challenges our models, suggesting either that galaxy formation was faster and more efficient than we thought, or that something crucial is missing from our understanding. The Hubble tension, the discrepancy between local and CMB measurements of cosmic expansion, might signal new physics, unknown particles, or evolution in dark energy. We don't know. The lithium abundance doesn't match predictions. The universe seems too uniform despite causally disconnected regions. There are mysteries nested within mysteries, puzzles that remain unsolved despite decades of research. So is the Big Bang Theory true? Yes, in every way that matters to science. It's true in that it accurately describes the observable history of the universe from fractions of a second after the initial event to the present day, 13.8 billion years later. It's true in that its predictions have been confirmed again and again by independent observations using different methods. It's true in that no alternative theory explains the evidence better. But it's incomplete. It's a chapter in a larger story we're still writing. It's the best answer we have, not the final answer, because in science, there are no final answers, only better questions. The Big Bang Theory is humanity's most ambitious intellectual achievement, an attempt to understand everything: the origin of matter and energy, the formation of structure from simplicity, the evolution of complexity from chaos, the emergence of stars and planets and life from a featureless fireball. It's a theory that spans 13.8 billion years and 93 billion light-years, from the smallest quantum fluctuations to the largest cosmic structures, from the first instant of time to the ultimate fate of all existence. Is it true? In its essential framework, yes. Will it be refined, modified, extended, and perhaps revolutionized by future discoveries? Almost certainly. The history of science suggests that today's answers become tomorrow's starting points. Consider how far we've come. In 1920, we thought the universe consisted only of the Milky Way. In 1929, Hubble discovered cosmic expansion. In 1965, Penzias and Wilson found the CMB. In 1998, astronomers discovered acceleration. In 2022, JWST revealed galaxies at cosmic dawn. Each generation thinks it's near the end of discovery, that the big questions are answered. Each generation is proven wrong by the next. What will we discover in the next century? What observations will challenge our current understanding? What technologies will reveal phenomena we can't yet imagine? Perhaps we'll detect primordial gravitational waves and confirm inflation. Perhaps we'll identify dark matter particles in laboratory experiments. Perhaps we'll develop a theory of quantum gravity that explains what happened at the singularity. Perhaps we'll find evidence of other universes or discover that we're living in a simulation. Or perhaps, more likely, we'll discover something completely unexpected, something that doesn't fit into any current category, something that forces us to reimagine the cosmos entirely. The universe is not only stranger than we imagine, it may be stranger than we can imagine, as biologist J.B.S. Haldane suggested. Our brains evolved to survive on African savannas, not to intuitively understand quantum mechanics or cosmic inflation. The fact that we can understand anything about the universe's origin is itself remarkable. Yet here we are, barely a century after learning that other galaxies exist, having traced cosmic history back to the first minutes, having photographed the universe in its infancy, having calculated its age to within 1% accuracy. We are the universe becoming conscious of itself, matter organized in such a way that it can contemplate its own origins. We are made of atoms forged in stellar cores, elements created in the Big Bang, energy that has existed since the beginning of time. We are, in Carl Sagan's phrase, star stuff pondering the stars. The Big Bang Theory tells us we live in a universe with a history, a universe that was born, that evolved, that will die. A universe that began inconceivably small and grew to inconceivable vastness. A universe that was once unimaginably hot and is now cold. A universe that was once perfectly uniform and is now structured into galaxies and stars and planets. A universe capable of producing complexity from simplicity, life from non-life, consciousness from unconsciousness, questions from questioners. Is the Big Bang Theory true? That's the wrong question. The right question is, what does the evidence tell us about the universe's nature, and what mysteries remain to be solved? The evidence tells us the universe had a beginning. It tells us we live in an expanding cosmos of unimaginable age and scale. It tells us that everything we see emerged from a hot, dense state through processes we're beginning to understand. But the mysteries are deeper than the answers. For every question answered, new questions emerge. For every mystery solved, deeper mysteries appear. What caused the Big Bang? We don't know. What is dark energy? We don't know. What is dark matter? We don't know. Are we alone in the multiverse? We don't know. Why does anything exist at all? We don't know. And that, perhaps, is the most profound truth. The universe remains fundamentally mysterious. After a century of revolutionary discoveries, after measuring cosmic history with extraordinary precision, after photographing galaxies at the edge of space and time, we've barely scratched the surface. The cosmos is vast. The questions are endless. The mysteries are infinite. The journey continues. And somewhere, right now, a young scientist is looking at data that doesn't quite fit, noticing an anomaly that everyone else overlooked, asking a question that will change everything. The next chapter is being written. The greatest discoveries may still lie ahead. The universe awaits.